Hey guys, welcome back to my channel. In this video, I'm going to be going over topic 2 of IB chemistry, and topic 2 is all about atomic structure. So if you guys are new to this series, which I'm doing, I'm going to be going over the understandings, applications, and skills, mainly that stuff, and guidance, but not so much utilization. I'm not going to be focusing on international mindedness or theory of knowledge because my assumption is that you guys are here to do some quick revision before an exam, so I'm not going to be going over this stuff, which is unlikely to get asked unlikely for you to get asked in an exam. And even if you do, they're quite straightforward concepts. So without further ado, let's get started on topic 2, atomic structure. So you might already be aware of most of topic 2.1, which focusing on the nucleus of the atom, and atoms have a nucleus which contains protons and neutrons. And protons we know are positively charged, and neutrons we know are neutrally charged. So when you have positive and neutral, neutral does not change the charge. We have a positively charged nucleus. And also we call protons and neutrons nucleons. Negatively charged electrons occupy the space outside the nucleus, and currently, if you haven't done topic 2 or learned much about it, you probably think that they are in orbits around. But in IB chemistry, we don't actually talk about orbits, we talk about orbitals. We'll go into that later. The mass spectrometer is used to determine the relative atomic mass of an element from its isotopic composition. So a mass spectrometer will come up further in topic 1123 as well, but it's just something that shows a graph like this, which has percentage, well, relative abundance. So relative abundance is going to be in terms of percentage, and you're going to have, I believe it's molecular fragments, and you're going to have these lines, right? In topic 2, we're going to be going over isotopes. So isotopes, we're going to have chlorine is a commonly used example. We have like chlorine 35, chlorine 34, and 33, 36. So we could have that stuff. I'm not sure if this is real. This is just an example, so take it with a grain of salt. So we have these percentages. See, we have these atomic masses and we have these percentage abundances. Using these, we can calculate the relative atomic mass. Notice in your periodic table, when you have the atomic mass of chlorine, it's a decimal place point. Even though we learned that the number of protons and neutrons in chlorine should add up to somewhere around 34, I believe. But in reality, it's actually like 34.99 or 33.99, something like that. We're looking at the isotopes and their relative abundance, and we're calculating a mean value. I'll make a video on this later on how to do the actual calculations, but if you're using this for revision, you probably had a spark in your brain which just reminded you how to do that calculation. Use of the nuclear symbol notation, so A is the number of protons and neutrons, Z is the number of protons, and in a neutral atom, so atoms are neutrally charged, ions are not neutral, they're charged, and electrons and protons are equal in an atom, so Z would equal the number of electrons in an atom. Ions, it's completely different. Calculation involves non-integer relative atomic masses and abundance of isotopes from given data. So non-integer, not whole number. So you're going to have to work out using calculations and the mass spectrometer results. You're going to have to work out the relative atomic mass. And you could be cheeky and think about in a paper too how you can basically look at the periodic table and work out the relative atomic mass of an atom or an element. But that's actually not how it works in IB. They actually can the final answer for a relative atomic mass question could be different from the actual relative atomic mass of the periodic table. So don't try to do that. Relative masses and charges of subatomic particles should be known. One proton is positive and mass is 1, neutron is 1, and electron has negligible mass, but sometimes it's 1 on 1,800, but it's just generally negligible. Specific examples of isotopes, you don't need to know that. So you don't need to know about like chlorine 35, carbon 14, but you probably hear that a lot. Operation of mass spectrometer, you don't have to know how it works. PET scans are quite interesting. So you have this molecule called a positron emitting molecule, which is quite complicated, but you put that substance in a person's body and it releases what we call positrons, and they're sort of radiation that we can detect and learn the 3D 3D inside of a person's body without having to cut them open, which is quite useful in medicine. Radioisotopes are used in nuclear medicine, so again, we are using nuclear stuff for medicine. and this is also X-rays and stuff like that, which give us insights into the structure inside the human body without having to cut someone open. It's quite helpful. And chemical clocks, so you can think about radioisotopes actually decompose, and they decompose at fixed time intervals generally. So um, by checking how much is decomposed of a substance, we can determine how old it is. So this is quite important in archaeology. Next, topic 2.2, we're looking at the electrons around an atom. Emission spectra are produced when photons are emitted from atoms as excited electrons return to a lower energy level. So right now at this point, you can think of electrons orbiting around the nucleus, and they are orbiting around in certain energy levels. So out, out, out. And when these electrons move from an inner to an outer energy level, they absorb photons or energy. But when they cannot stay in this excited form, we call it the excited form forever. So they fall back down, and when they fall back down to the lower energy level, they release energy, and commonly is released as light or photons, and we can see a light change. So if we look at an emission spectra, it's sort of like this black background with all these hashes. So you could have like I'm not going to draw one out, but you could have just like green, blue, red, and because of these distinct lines, it suggests that atoms themselves have electrons in distinct energy levels, which is quite cool when you think about it, because you think that in the molecular scale, things are sort of blended together and there's like ill-defined boundaries, but there are actually very well-defined boundaries in the atomic scale of things. The main energy level or shell is an integer number n and can hold maximum number of 2n squared. So that's just something we need to remember. So if you're looking at the shell number, so shell number is, so if you have the nucleus, this is shell 1, this is shell 2, this is shell 3. So shell number 1 can hold 2 times 1 squared, which is just 2. And shell number 2 can hold 8, etc. A more detailed model. So this is when we're talking about what we call orbitals. And orbitals are regions of electron density or regions around the nucleus of an atom which have a high probability of finding an electron. So these orbitals are quite complicated, and if you're watching this video and you have no idea what orbitals are, I recommend you do some further study on orbitals, because I'm not going to be able to explain this in the time given, because orbitals are quite a complicated topic. Sublevels, so you need to know about the S, P, D, and F orbitals. They are based on, they make sense. If you study this, you'll understand why we have the S block, P block, D block, F block in the periodic table. But S, P, D, F, that's basically the order from low to increasing energy, and also from smaller to larger orbital size. Sublevels contain fixed number of orbitals, regions of space with a high probability. We already said that. Each orbital has a defined energy state for a given electron configuration and can hold 2 electrons. So each orbital, right, each SP levels, right, have different numbers of orbitals. S has 1 orbital, P has 3, D has 5, and F, I think 7. I'm not sure about that, but you won't have to know much about F. And each of these orbitals holds two electrons. Description of the relationships between color, wavelength, frequency, and energy across electromagnetic spectrum. So the electromagnetic spectrum goes from like X-rays to ultraviolet, radio waves, something like that. You're just gonna have to remember that and do a bit of study on it, and you can see that wavelength is inversely proportional, or when wavelength increases, frequency decreases. So that's the main relationship you need to know, and think about color and how that relates to wavelength of light. Distinction between continuous spectrum and line spectrum. So continuous spectrum shows an unbroken series, whereas line spectrum shows a broken, distinguished series. So if you look at astronomy, you can see light emitted from stars can be used to identify the composition and the molecules contained in the stars themselves. Atomic absorption spectra is very sensitive means of determining presence and concentration of metallic elements. Okay, so absorption spectrum is, or spectroscopy is really cool when we think about um, metals, because metals can lead to lots of colored compounds, and we're going to talk about the why in topic 3. So watch my video on topic 3 if you want to know why that's the case. Description of the emission spectrum of hydrogen includes relationship between lines. Okay, so when you have energy transitions to the first level, so when you have transitions of electrons from higher energy to the first level, we call that the Lyman series, and this releases ultraviolet light. This is UV. Second one we call that the Passion series, I believe. No, Balmer series, and this one is visible light, visible light. And third one is called the Passion series, and this one is infrared light. So you're gonna have to remember those. Recognition the shapes of the S and P orbitals. So S orbital is kind of like a dumbbell shape, and this one is kind of weird. This one is a whole other video. So you're gonna have like the orbitals are sort of like this, and this. Whereas S orbitals are sorry. This is the P orbitals are the dumbbell. S orbitals are just like a circle around the a circular region around the nucleus. Afbel principle is the idea that when electrons in an atom are filled from the inside lower energy shells to the outer energy shells. So you're not going to have an electron with four electrons. Sorry, we're not going to have an atom with four electrons in the second energy level and a zero in the first energy level. If there are going to be electrons in the second energy level, there'll always be some in the first energy level. We fill from the lower to the higher energy. Hund's rule is the idea that orbitals. Remember how I said we have orbitals like this? So S has one orbital, P has three orbitals, etc. So each of these orbitals can occupy two electrons. We represent them like this. And Hund's rule is the idea that electrons prefer to be singly occupied rather than singly occupied in preference to being doubly occupied. Well, doubly occupied means that you have two negative charges really close to each other, so intellectual repulsion increases, leading to higher energy, and this is unfavorable for an electron. So we prefer like single occupation of um, of electron orbitals. However, when you are filling up with more and more electrons, you do get doubly occupied orbitals. Next, the Pauli exclusion principle is the idea. So you saw how I drew the electrons like that. Those represent opposite spins. So Pauli exclusion principle says that if two electrons occupy the same orbital, they're going to have opposite spins. So you're going to have to draw them like that. Details of the electromagnetic spectrum. So it's already given. That's why don't have it memorized. And it's already given in the data booklet. Just remember the relationships between wavelength and frequency as a starting point. Names of different series in the hydrogen line spectrum. Okay, so you don't need to remember Balmer, Lyman, and Paschen series, but you need to remember the type of light that they do emit. And full electron configurations, this can be done in an orbital's video, but you just gotta write it like this. So you have one S represents the first S orbital, and 2 represents the number of electrons in that orbital level, energy level. So 2S is the second S orbital, and this 2 represents the number of electrons in it. And 2P is the second P orbital, and there's 6 electrons. 3P, we have 4 electrons. So it's not a full 3p orbital. So we're not saying that 3p can only occupy 4. It's just that neon has only 4, so it's not fully occupied. Sorry, it's not neon actually. This is the a condensed electron configuration with the halogen notation. So you know how in the periodic table you have halogens at the end of the row? Well, halogens represent a completely filled electron orbital level, right? Because when you move from neon to sodium, when you move from neon to sodium, you're going to have a new energy level. So you can represent sodium like this. You can write this, and here square brackets don't mean concentration, they mean core or neon core, which means the core electrons from neon are applied to this atom as well. And you have, I believe, is 3s and then 1 for sodium. This one would be something in the third period. Orbital diagrams should be used to represent. So earlier I used orbital diagrams to show you how to do how to represent the electrons in an atom. And orbital diagrams, again, I make a video on orbitals and explain the concept behind it. If you don't understand what orbitals are, you should probably look it up and get quite familiar with it because they are a steep learning curve. Electron configurations of chromium and copper are exceptions, should be covered. So chromium and copper, the interesting thing about this is because of Hund's rule, they have so chromium, the electron configuration, let me write it here. So you have, it's going to be an argon core. So I'm going to write it like this, argon core. And then you'd expect it to be like this, 4s2 and then 3d4. However, this is not the case because instead of having, so the 3D orbitals consist of 5 orbitals, 3D sublevel. So we're going to have this, all right? We're going to have this. And then the 4s part, we're going to have this. And remember Hund's rule, how we said it's favorable for a single occupation? Well, what happens is chromium can actually promote one electron like that. So it's 6 electrons. So we had 6 electrons earlier are actually written like this. So it's going to be written like this, and this is lower energy, more favorable. Same thing with copper. So I'm going to leave a challenge to you. You guys should try and deduce the electron configuration of copper based on the same rule. And this is all about Hund's rule. Hund's rule. So this is where it's actually applied. So Hund's rule comes in here. And other than that, that's going to be it for all of topic 2 in IB chemistry. So topic 12 is the HL component of IB chemistry, and I'm going to be going over that later when I'm covering all the HL components. But if you're an SL or HL student, this topic applied to you. And if you guys enjoyed this video and learned something new, please don't forget to like and subscribe. It really helps out the channel. And if you have any urgent topics you want me to cover for a chemistry exam that you have coming soon, please comment down below on this video and I'll make sure to make a video on it. Other than that, see you guys in a future video.